Stepper motors are classified as brushless DC electric motors. They divide full rotation into an equal number of steps. They are used in many applications in daily life that include CD players, electric tools, and automation equipments. As the name suggests, each pulse of electricity produces one step of rotational motion. For this exercise, we'll discover the basics of stepper motor technology, beginning with the brushless DC motors. Unlike DC brushless motor do not utilize brushes to control current. Permanent magnets bonded directly to the rotor of the brushless DC motor create rotational motion as current passes through the stator. A rotating magnetic field is formed by electrical pulse generated by a converter as the rotor turns. A rotor position sensor provides feedback to the converter so the required stator field rotational sequence is maintained. The change in sensor state report back to the converter, which continuously switches the phase to the windings to keep the motor turning. The sequence is further explained. Here the Hall effect sensor turn on. Coils are energized by the converter. The sequence is further explained here when the Hall effect sensor turn on, creating the magnetic field to turn the rotor. The sequence is repeated with the next set of Hall effect sensor and coils to continue rotation. With the DC brushless motor being the foundation of stepper motor, let's look at how stepper works. Stepper motor are so named because each pulse of electricity turns the motor one step. A simple stepper motor system is comprised of four elements. The user interface allows the operator to input motion parameters such as speed, distance, and directions. Example at an interface would be programmable logic controller or data entry terminal. The number of steps the motor turns is equal to the number of pulses transmitted to the driver. The stepper motor is a brushless electric motor that converts pulse into mechanical shaft rotation. Each pulse moves the shaft through a fixed angle defined by the multiple tooth electromagnets arranged around a gear-shaped motor. Stepper motors have three-step modes of operation that includes full, half, and micro stepping. The type of step made output to any stepper motor is dependent on the design of the driver. The driver also controls both the step angle and speed of the motor by switching the field coils in a set sequence. For full step made operation, energizing each set of coils sequentially. The rotor can be made to rotate or step from one position to the next by an angle determined by its step angle. Shaft rotation is achieved by energizing both windings while reversing the current alternately. Switching coil A, B, C, D, one coil at a time repeatedly will rotate the rotor in the forward direction. In this example, there are 6 steps arranged on the rotor 60 degrees apart. 24 steps are required to make a full rotation at 15-degree increment. 4 half steps move the stepper motor resolution can be doubled by alternating the switching of coils. Half stepping occurs when one winding is energized and then 2 windings are energized alternately, causing the rotor to rotate at half the distance. Switching coil in this combination will rotate in the reverse direction. As you can see in this example, 48 steps are required to make a full rotation at 7.5 degree increment. Microstepping controls the current in the motor windings to a degree that further subdivides the number of positions between poles to achieve microsteps. The coils are only partially energized as we apply a maximum voltage of 5 volt DC to coil and a maximum voltage of 0 volt DC to coil B. Motor position 1 will line up, reducing the voltage to coil A and increasing voltage to coil B. The rotor will begin to rotate in a clockwise direction and continue until the voltage is 0 at coil A and 5 at coil B. This process continues at all coils within the stator to provide accurate positioning. As you can see in this example, 120 steps are required to make a full rotation at 3-degree increment.